So welcome to the YouTube channel Shanti-Peace for Mathematics. So in my previous video probably you have learned about algebraic properties of complex numbers, in which we have discussed what is a commutative law, what is a commutative law for addition and multiplication, what is associative law for complex number, what is the inverse, additive inverse, what is the multiplicative inverse and their properties, and how to find out the additive and inverse, and all sort of things we have discussed in the previous lecture. So today in this lecture we are going to discuss about the vector and the moduli. So the basically we are discussing the first thing is what is the geometrical interpretation of complex number. Any non-zero complex number z is equal to x plus iy with the directed line segment or a vector from the origin to the point xy that represent z in. So it says that the any non-zero complex number in a complex plane, it is a directed line segment or a vector from the origin to the point xy. So if you can see this complex plane is also known as a organ diagram. So we refer a z is a directed line segment or it is a vector from the origin. So what we refer as a z is the in xy plane. So if you can consider this is your x axis and this will be your y axis, then if this is the point xy, then this line which is the z equal to x plus iy, which is your complex number. So it is a vector or a directed line segment. For example, if you consider as an example, if I have x and y axis, and if I have a point z is equal to 3 plus I, then we need to first look at the point where is the 3 1. So the 3 1 point that will be here, this is 3, and 1 will be here, so this is the point, and the directed line segment from origin to 3 1 will be your complex number 3 plus I. So now the next thing that we can see is what is the geometrical interpretation of z1 plus z2. If you have the two complex numbers z1 and z2, z1 will be x1 plus iy1 and z2 will be x2 plus iy2, then the sum, we know that the sum z1 plus z2 is defined as x1 plus x2 plus I y1 plus y2, and this also correspond to a point x1 plus x2 comma y1 plus y. So we'll see by an example first, and then we'll try to see what will be the geometrical interpretation of the addition. So let's have z1 will be 1 plus I and z2 will be 2 plus I. So let us try to draw that 2 points or 2 line segment, directed line segment or a complex number. If this is your x axis and this is your y axis, so we know that if this is the 1, this will be 2, and here it is 3. If I consider this is as 1, and that the z1 will be 1 1 point, so this is the 1 1 point that you have, that is the line segment. So this is 1 plus I, and z2 will be 2 plus I, so z2 will be here, that is 2 plus I. Z3 will be 3 plus 2I as per the definition, which is nothing but the z1 plus z2. So if you try to draw the z1 plus z2, this is 3 and here it will be 2, plus z2. So this point is actually x1 plus x2 comma y1 plus y. So another way you can see that if I copy this z1 over here, then what you will get here, it is z1, so that is z1. So there is z2 plus z1, which will be this vector. So actually what you have is z1 plus z2. If you go in this direction, z1 plus z2, and if you go in other way, that is z2 plus z1. So what is this will gives you? It is actually another proof or geometrical proof or commutative property of addition. So after seeing this, one can ask a question: what is a geometrical interpretation of z1 into z2? So what is your answer? Think over it. If you have a geometrical interpretation of z1 plus z2, what will be the geometrical interpretation of z1 into z2? So the product of two complex number z1 and z2 is itself a complex number represented by a vector. So the product of these two will be again a vector, and that vector lies in the same plane as vector for z1 and z2. So this vector z1 into z2 will be lies in the same plane. Now if you can have the product in ordinary vector calculus or vector analysis, there will be two kinds of products are there: a vector product and scalar product. That is, the scalar product means v bar dot u bar, that is a pointwise multiplication is, and cross product you probably have learned in your 12th standard. So this product will not represent any of these two, so it is totally different than these two products. So that is, we can write as a note: this product is neither the scalar nor the vector product used in ordinary vector analysis. So you cannot compare these two things. So after this discussing this much geometrical interpretation and all sort of things of vectors, we like to define a modulus, or it's also known as absolute value. So actually the vector interpretation of complex number especially help into expanding the concept of absolute value of a real number to a complex plane. What you can see, the non-negative number mod z, called a modulus or absolute value of z is equal to xy, is the distance of the complex number from origin, and hence mod z is equal to square root of x square plus y square. So what is that? A modulus is nothing but the distance from the point z is equal to x from origin. So geometrically, if you can see, if this is your y axis, if this is your x axis, and if this is the point z is equal to xy, so that is the vector or line segment, the distance from here to there, that is the mod z that you have. Now another question I like to ask here: if I give you two number 3 plus 2i and 5 plus 2i, which of the above number is bigger? So what is your answer for this question? So the answer to this question that you can give is, it is meaningless question. This question itself is meaningless. With that we will write a note here. Why? Because if you have two complex number, they are in the plane, they are the two line segments, you cannot compare. Or you have a two vector, you cannot compare the which vector is bigger. Yeah, we can talk about bigger in the length, but we cannot talk about the vector as a vector they are bigger. Okay, so this statement, the inequality z1 less than z2 is meaningless unless both z1 and z2 are real. The statement mod of z1 less than mod of z2 means that this has a meaning. Why? Because mod z1 and mod z2 are the real number, so they have a meaning. That means that how far the distance is from origin, the point z1 is closer to the origin that the point z2 is. Okay, so that means that these 2 points are near to each other. z1 is near to z2 as you have. For example, let us have the example. So if I consider the number z1 as minus 3 plus 2i, then mode of z1 will be square root of minus 3 square plus 2 square, that will be 9 plus 4, that is square root of 13. And if I consider z2 will be 2 plus 4i, and so z2 will be square root of 4 plus 16, that is 2 square plus 4 square, and that will be square root of 20. We say from this that root of 20 obviously bigger than root of 20 is obviously bigger than root of 13. So what we can say is that minus 3 plus 2i is closer to the origin that 2 plus 4i is. Now the next concept that we'll discuss about, that is the distance between 2 points. Let us consider A, which is x1 y1, and B point, which is x2 y2. If there are the 2 points is given to you, then you know that the distance between this A and B will be have square root of x1 minus x2 square plus y1 minus y2 square. And you can observe what will be this x1 minus x2 comma y1 minus y2 will be the z1 minus z2, as we have discussed in my previous video. And if you use the definition of modulus, you can observe that this is nothing but the mode of z1 minus z2. So ultimately what we can say is the distance between any 2 points x1 y1 and x2 y2 is nothing but the mode of z1 minus z2, where this will be the z1 and this is the z2. That you can observe very clearly. Okay, because if you can have z1 is x1 plus I y1 and z2 will be x2 plus I y2, then you know that z1 minus z2 will be x1 minus x2 plus I y1 minus y2, and mode of this will be square root of x1 minus x2 square plus y1 minus y2 square. So that is the distance between 2 points. What is the geometrical interpretation of additive inverse of a complex number? That means what will be the geometrical representation of minus? So if you have given, this will be the y-axis and this is your x-axis. If this is your z, that is x comma y, or z will be x plus iy, then minus z, you know that minus z will be minus x minus y. So minus x minus y, obviously it comes here, this is the minus z. So my question is, what will be the geometrical interpretation of z1 minus z2, or what is the how geometrically the distance between 2 points is mode of z1 minus. So with that, for doing that, we'll consider this is as y-axis and this will be your x-axis. If I consider this is as x1 y1, that is your z1. If I consider this is as z2, that is x2 comma y2, what we need to find out is z1 minus z2. z1 minus z2 we can write z1 plus minus of z2. So we already know what is the geometrical interpretation of z1 plus z2. So what is the minus z2? The minus z2 is here on the opposite side of z2. This is the minus z2 you will have here. Now what I am doing is, I am copying this minus z2 and place it here in place of in opposite direction. So in the reverse direction, this is z2, which is the same length, and in the reverse direction the minus z2 is. So I am copying that minus z2 here, minus z2 that I am copying here. So what is z1 minus z2? That is this z1, this z1, plus minus z2. So that is this vector. So z1 minus z2 will be this z1 minus z2, which is same as this vector that we have here, z1 minus z2. This two vectors, this vector and this vector are parallel and they are in the same length. So this is the z1 minus z2 you will have. So what is this now? That means the distance between these two will be mode of z1 minus z2 is. So that is the geometrical interpretation of z1 minus z2 that we have. The next, by seeing this, what will be the locus of circle? What is the definition of a circle you have? If you have a fixed point, and the set of all points which are equidistant from this point, it's called the circle. So this distance is fixed, let's say small r. If this point is z0, then set of all points which are equidistant from this z0, it's called the circle. So it is the set of all points, let's say z, which are equidistant. As we have the distance between any point on this set will be defined by z, then the set distance between z and z0, if this is fixed, then it is called the locus of the circle. So the complex number z corresponding to the point lying in on the circle with center z0 and radius small r satisfies the equation mod z minus z0 equal to r. And conversely also we refer that the set of points implies the circle itself. For example, if I consider an example, z minus 4 plus 1 plus 4i equal to 2 represent the circle whose center is 1 comma minus 4 and radius will be 2. So I'm giving you this is exercise for you, what is the locus of ellipse. Now the next thing that we are discussing is we denote a real part of z as x and imaginary part of z as y if z is equal to x plus iy. So z we can write as the real part of z plus I imaginary part of it. So if we have this, then mod of z we can write as square root of a real part of z square plus imaginary part of z square. So now we can observe here one inequality which is always true. First thing that we can observe is a real part of z is always less than or equal to mod of real part of z, and this mod of real part of z is always less than or equal to square root of real part of z square plus imaginary part of z. Why? Because what I actually did is I have just write down a real part of z is always less than or equal to a real part of z square, and then I have obviously this will be less than or equal to this quantity, and this quantity you have that is nothing but the mod of z. So combine this, what we can say is a real part of z is less than or equal to mod of real part of z is less than or equal to mod z. Similarly, we can say that imaginary part of z is less than or equal to mod of imaginary part of z is less than or equal to mod z. So with this two inequality we'll move further. We'll discuss about what is the triangle inequality. So what is triangle inequality? For any two complex number z1 and z2, to that mod of z1 plus z2 is less than or equal to mod z1 plus mod z2. We'll prove this result via two ways. The one proof I am giving you now, for the another proof you have to wait for my next video. In this, let us first understand what is this property or what is this triangle inequality geometrical. So this result is actually obvious because that is actually correspond to any triangle if you can have. Now in the triangle, if this is your A, B, C, if this is the triangle, then probably you know that the any of this side, let us take AC, will be always smaller than the sum of other two sides, that is AB plus BC. This is always true, that you probably know. So this is also a same thing geometric way. If you can see, what is the mode Z1? So if you can see geometrically, the mode Z1 is this, that is this distance from this one. If this is x1 y1, the mode Z2 will be this one. If this point is x2 y2, then you know that here we have write down the same length as Z2 here, and Z1 plus Z2 will be this. So that is the Z1 plus Z2, which is the, if I take distance bit from the origin, that then this will be the mode of Z1 Z2. If I consider this is as O, this will be A and this is B, then this is in this triangle OAB. Obviously the one side, that is Z1 plus Z2, is less than or equal to sum of other two sides, that is OA plus AB. That is exactly a triangle inequality is. So here I am giving you algebraic proof. This is the geometrical proof of the triangle inequality. I am giving you a geometrical proof. The third proof, for that you have to wait for my next video. So here I am considering, to give the algebraic proof, I am considering Z1 as x1 y1, or you may write as x1 plus I y1, and Z2 as x2 plus y2, or x2 plus I y2. Now what we want to prove? We want to prove that mode of Z1 plus Z2 is less than or equal to mode Z1 plus mode Z2. If this is equivalent to right, if this notation we have discussed, then Z1 plus Z2 is x1 plus x2 and y1 plus y2, and mode of that will gives you a square root of x1 plus x2 square plus y1 plus y2 square, less than or equal to mode of Z1 is x1 square plus y1 square plus mode of Z2 will be x2 square plus y2 square. If I am making a square both side, this statement is also equivalent to expanding this brackets. What we can say is, it is x1 square plus 2 times x1 x2 plus x2 square plus y1 square plus 2 times y1 y2 plus y2 square, which is less than or equal to, if you can consider this is as A, this quantity, and this quantity as B, and if you square them, then the square of A square will be x1 square plus y1 square plus 2 times square root of x1 square plus y1 square and square root of x2 square plus y2 square plus x2 square plus y2 square, that is the square of B you have. Now what we can observe is this x1 is cancel out with this x1, x2 will cancel out with x2, y1 is cancel out with y1, y2 square will cancel out with y2. What is the quantity is left here is this 2 is also common from this 2 quantity, and that's cancel with this. So what is the things you will left is x1 x2 plus y1 y2 is less than or equal to square root of x1 square plus y1 square into square root of x2 square plus y2 square. Now again I am making a square both side. What you will have is x1 square x2 square plus 2 times x1 x2 y1 y2 plus y1 square y2 square less than or equal to x1 square, and if I do the square both side and I am multiplying this to brackets that you have, what you will have is this x1 is multiplied to x, so x1 plus x1 square y2 square plus y1 square x2 square plus y1 square y2 square. What you can have is this x1 square x2 square is cancelled with this x1 square x2 square, and y1 square y2 square is cancelled with this y1 square y2. So what is the things we'll have? We can rewrite that. That is x1 square y2 square minus 2 times x1 x2 y1 y2 plus y1 square x2 square greater than or equal to 0, and by taking this quantity on the other side. And what will be this is actually x1 y2 minus y1 x2 whole square, which is greater than or equal to 0, and which is always true. So what we have, if this quantity is always true, so and the above all statements are true, so triangle inequality is true for any complex number. Now the next thing is next property I can say, mode of z1 minus mode of z2 whole mode is less than or equal to mode of z1 minus z2, which is less than or equal to mode z1 plus mode z2 for every z1 z2. So obviously this inequality is easy to see. How we can see that? So mode of z1 minus z2 is equal to z1 plus minus z2. So by triangle inequality we can write down this is z1 plus minus of z2, and minus of z2, mode of minus of z2 by definition will be mode of z1 plus mode z2. Now for the another inequality, what we can see is we will start with z1. I am subtracting and adding z2 here. So I am subtracting z2 and adding that. By triangle inequality we can write down this is z1 minus z2 plus z2, and therefore now interchanging the role of z1 and z2 in above, we get mode z2 minus z1 less than or equal to mode of z2 minus z1. Now mode of z2 minus z1, that we can write as minus of z1 minus z2, and minus of z1 minus z2 is minus of z1 minus z2. If I call it this is as a statement 1, and if I call this is as a statement 2, then from 1 and 2 what we can write is mode of z1 minus mode of z2 is less than or equal to mode of z1 minus z2. So that proves the statement. Now we can also write, so because of minus of mode z2 is mode of z2, one can replace z2 by minus z2 in above inequality. What we get is mode of z1 minus mode of z2. Because of minus z2 will be mode of minus z2 will be mode z, that is less than or equal to z1 plus z2, and by triangle inequality we can write down this is mode of z1 plus z2. So combine both this statement, what we can write is mode of z1 minus mode z2 is less than or equal to z1 plus or minus z2 is less than or equal to mode z1 plus mode z2. This is true for any z1 and z2 as a complex number. Now the next result I am giving you as an exercise or homework. So I am making as a homework. If z1, z2 up to zn are complex numbers, prove that z1 mode of z1 plus z2 up to zn is less than or equal to mode z1 plus mode z2 up to so on mode zn for any n belongs to natural number. For any n this is true. So the hint is obviously PMI, that is principle of mathematical induction. So you can prove this result by induction. Now with the things this I am giving you as some exercise or examples. Let us try to do some examples. So find the upper bound and lower bound of mode z1 minus z2 when mode z is 1. So obviously what is this mode z1 mode z is equal to 1 represents is a circle, as I have discussed above, because it is z minus 0. So it is a circle with center 0 and radius 1. So the question is what will be the upper maximum or and minimum value of this on that circle. So the answer to this question, we can use a triangle inequality. So we can write down this is as mode of z plus minus z2, and you know that the mode z is 1 and minus of mode 2 will be 2, so this is 3. So the maximum value of mode of z minus 2 is 3, and z minus 2 is by another inequality which we have discussed, we can write as this, that we can write as mod z1 minus 1, sorry, minus 2, that we can write as 1 minus 2, which is 1, because minus 1, which will be 1. So that means by combine both of this, what we can write is 1 is less than or equal to 1 minus 2, sorry, z minus 2, which is less than or equal to 3. So this is the lower bound and this is upper bound when mod z equal to 1. Next example that we can discuss is find the upper bound of the function z square plus 3 upon z square minus z minus 6 when mod z equal to. So here what is the two things is, here just question is to find out what is the upper bound of this. Okay, so what we can observe here, z square plus 3 upon z square minus z minus 6, which we can write down as is mod of z2 plus z3 upon mod of z square minus z minus 6. Here actually we have using this result, mod of z1 upon z2 will be mod z1 upon mod z2, which is less than or equal to mod z square plus 3 upon mod of z square minus z minus 6. Here we are using the triangle inequality. That further we can write as z square plus 3 upon mod z square minus z minus 6. That is the things we are using is z raised to n is mod of z whole raised to n for any n belongs to. Now in the denominator what we have, so numerator is as mod z is equal to 1, we can write this is 1 plus 3, so this is 1 plus 3 upon mod z square minus z minus 6. Now the question is what is the, if you want to find out upper bound, still if you want to write down this is less than or equal to something, you have to find out what is this greater than or equal to is. So for that I am just doing here z square minus z minus 6, I can factor x plus iy. By triangle inequality we can write this is mod x plus mod iy, which is right as mod x plus mod of iy, because the mod of I is 1 using, so that is the inequality we'll have using the arithmetic and geometric mean inequality, that is AMGM inequality. So what is AMGM inequality? Which says that mod of x square plus mod of y square is greater than or equal to 2 times mod of x mod of y. So what I am doing is I am adding both side by x square plus y square. So that is x square plus y square I am adding here on this side and the also in the other side. This side it is 2 times mod of x square mod of y square. The other side is mod of x plus mod of y whole square. This side is nothing but the mod of z square is greater than or equal to mod of x plus mod of y whole square, because mod of x square you can write as x square. So due to that, this will be x square, this will be y square, so that is mod of z square, x square plus y square, mod of z square. So I am taking up or non-negative square root both side. What we have is mod of x plus mod of y by 2 is less than or equal to mod by taking positive square root. So by doing this last property of this lecture, after giving one exercise, will wind up for this video. Prove that, this is the exercise that you can do. Prove that 1 upon mod of z raised to 4 plus 5z cube plus 8z square plus 11z plus 90 is less than or equal to 1 upon 4000 when mod z is equal to 10. So what we have did today is we have discussed about the geometrical interpretation of complex number, addition of a complex number. We also seen the how the z minus z1 minus z2 is the geometrical representation. Second one, we have discussed about the modulus. The modulus is also, we have seen the geometrical interpretation of the modulus, its different property of the modulus and some results on a modulus. Basically we have seen the triangle inequality. So in the triangle inequality, what I say it is I will give you some proof in my next video. Here we have seen one geometrical proof of triangle inequality, also algebraic proof of a triangle inequality, and some results or some examples based on triangle inequality to find out the lower bound and the upper bound of some quantities are given. So that's it for this video. Thank you very much for watching me or listening me. Please if you have liked this video, please like, subscribe to my YouTube channel, and please give your comment below for if you have any questions. Thank you very much.